What is the meaning of recursion here? So we are calling the same function again is nothing but recursion. See, this is the path taken in this algorithm to reach the goal node G. Breadth first search is going to take the shortest path with respect to the lowest cost. This is the definition, and this is the difference between the DFS, depth first search, as well as depth limited search. Dear students, welcome to computer science classes. I am Ravi Kumar KR, lecturer in computer science, Vidhyaashram Postgrad College, Temple of Excellence, MYSURU. Student, let us start our discussion with the chapter or unit problem solving by search. In this session, we are going to talk about different types of search algorithm. So they are breadth first search or BFS, depth first search or DFS, and depth limited search. These are the concepts to be covered in this session. Now let us see what is the definition of depth first search, one type of algorithm. So it can be recursive or non-recursive. So what is the meaning of recursion here? So we are calling the same function again is nothing but recursion. So that concept we are using here. So it can be recursive or non-recursive. It is also an algorithm traversing or search tree or graph data structure. So we are implementing this type of algorithm through a data structure that is a non-linear data structure, either a tree or graph. It starts at the root node, means in this search algorithm, the search operation starts from the beginning or at the root node. It goes through the branch nodes and then returns, means it goes through the branch node, means it's going to traverse over the tree or traverse in the tree and reach the destination. It is implemented using stack data structure, and it works on the concept of last in first out, LIFO. So stack is a data structure which works on LIFO concept. See, these are the definition of depth first search. Now let us see the diagram here. So this is, this is a tree data structure, and here we can see there are levels here. So here 1, level 0, we start with 0, 1, 2 and 3. There are 3 levels, 1, 0, 1, 2 and 3. There are 3 levels in this data structure. So what is meaning of depth first search? In that case, in this algorithm, suppose if G is the goal node. Here, if you take G is the goal node. So as per the definition, this starts with the root node, that is S. S is the root node. So it starts searching from the root node and traversing the different nodes of a tree to reach the goal destination. As the name itself, depth first search, it is getting to the last node of the tree, or it gets into number of levels to reach the goal. That is the reason we say depth first search. So accordingly, if you look at this, if you take this example here, so if I want to reach the goal G, first from S, it has to traverse to A, and from A to B, and B to D, and after that D. This is the last node, that is the leaf node, and from D to E, and E to C, and C to G. See, this is the path taken by this algorithm to reach the destination G or the goal node G. So this is the, now let us see in the next slide what are all the, how is going to traverse. So traverse the tree deepest node first. Deepest node first in the sense is going to reach the last node till it gets the solution, or until it reaches the goal node. Now the path taken by the algorithm in this example, S, A, B, D, and here backtrack is there. See, what is the meaning of backtrack here? After reaching D, there is no further nodes to be continued. It has to go back to B, from here from B and again to E and to C. So this is the meaning of backtracking. Backtracking operation is there in this algorithm. E, C, finally G, that is the goal node. See, this is the path taken in this algorithm to reach the goal node G. As we have seen in the previous session, so we have to consider the 4 important factors to know the quality of this type of algorithm, or we have to consider the 4 factors. One is completeness. So what about this completeness of this algorithm? See, it is going to complete within the finite state space. So this algorithm is a completeness, or is going to complete, or is going to reach the goal within the finite state space. If I say state space, number of levels. Next, what is the time complexity? How do we represent it? It is the one, it is n squared, n cube, and n to the power of m, where m is the maximum depth of any node. So in the previous example, so from here to here, D, here D, this is level 3. Level 3 is the depth of this node D or G. So that is the meaning of depth of a tree. Then space complexity, it is the order of B and BM. Here M is nothing but depth of the tree. Next point is optimal. It is not optimal. So this algorithm is not optimal because it may generate large number of steps and chances of going to infinite leap. So that is the meaning of recursive or non-recursive. It may go for infinite loop, where it means there is no end for infinite loop. So it keeps on searching for goal or searching for a goal node, but it may succeed or it may not succeed. That is why it is not optimal. So this algorithm is not optimal. In the next slide, we will see another type of algorithm, that is breadth first search, that is BFS. So look at the definition of this. So here it starts from the root node, that is the then neighboring nodes first, and move towards the next level neighbors. So this is the difference between this one and the previous one. In the previous one, that is depth first algorithm, is going to the depth until it reaches the goal. But in this breadth first algorithm, it start from the root and it traversing to neighboring nodes, move towards the next level neighbors. It generate one tree at a time until the solution is found. It's going to look for a particular path until it reaches the destination. And it can be implemented using FIFO queue data structure. Using FIFO, that is queue data structure. So queue is a data structure. It works on the principle of FIFO, means first in, first out. So it can be implemented using queue data structure. Now this method provides shortest path to the solution. So breadth first search, that meaning is that it's going to provide the shortest path to the solution, whereas if you look at the previous example, it's going to take the long route, or it takes the long path to reach the destination. Now if you look at this example, now look at the diagram for breadth first algorithm. See here, this is the root node, this is the root node, and here is G, this is goal node, and here is also goal. This is the goal node. If you compare this with the previous one, if you look at the previous algorithm, it used to take deepest node first. This was the algorithm, but breadth first search is going to take the shortest path with respect to the lowest cost. So accordingly, to reach goal here, it takes the path S, D and G. So it takes only, there are two nodes to cross or traverse to reach the destination. Now we will see the definitions in the next slide, or the terminologies of this breadth first search. So here, as we have seen, the path S, D, G. So here S, D, G. So it's going to reach the destination. Next one is time complexity. means the amount of time taken by an algorithm to reach the destination. It is equal to number of nodes traversed in the BFS until the shallowest solution. That is the definition of time complexity. Next, space complexity. It is equal to how large can be fringe get. That is the definition of this. Then completeness. So it is complete. Meaning for a given search tree, it will come up with the solution if it exists. So means if the solution is exist, though it's going to find a solution, then we say this algorithm is complete or completeness. Optimality. So it is optimal as long as the cost of edges are equal. Means as we have seen, it is going to take the shortest path first or shortest path to reach the goal. So based on the cost, that is called the path cost. So it is optimal. Now what is the drawback of this? Drawback of breadth first algorithm. So here each level of nodes is saved for creating next one. It consumes lot of memory space. So space requirement to store node is exponential. Means this is the point of space complexity. It requires more space. Now its complexity depends on number of nodes. It can check duplicate nodes. See, these are the drawbacks of this algorithm. In the next slide, we will see another type of algorithm, that is depth limited search. Depth limited search algorithm. So in the first one, what you have seen, there is a depth first algorithm. This is depth limited search algorithm. Now let us see the definition of this. So here it is a modified version of depth first search that imposes a limit on the depth of the search. This is the definition, and this is a difference between the DFS, depth first search, as well as depth limited search. And in this algorithm, we are going to define the limit. So we are going to define the limit of for an algorithm. So this particular algorithm search for a goal or search for the destination within the limit set at the beginning. That is the difference between this as well as depth first search. It means that algorithm will only explore nodes up to the certain depth. Means it's going to explore or it's going to traverse until it reaches the limit or mentioned at the beginning of the algorithm. Next one, it is more efficient and preventing it from going down excessively deep paths that are unlikely to lead to the goal. Means it is not going to follow the deepest path to reach the goal here. That is why it is more efficient as compared to depth first search. Next, by setting a maximum depth limit, it aims to improve the efficiency and ensure more manageable search time. So by ensuring or by setting the maximum depth goal, it is more efficient. See, these are the definitions for depth limited search algorithm. Now look at the diagram now. So in this example, as we have seen in the previous slides, so this is the diagram. See, this is the S is the as usually this is the root, and see, suppose we say let J be the goal node. So to reach goal node here, so we have the limit set is, for example, limit 2 or level 2 is the limit set by the algorithm. So in that case, so this algorithm traverses till the level 2. If it is find the solution or it find the goal, then it is completed or is a completeness. Suppose there are chances that it may not reach the goal within the time, within the limit set by the user or set by the algorithm. So accordingly, in this example, so level is 2. That is the limit we have set. In that case, is going to search only level 0, 1 and 2. It may not go to the next level, that is level 3. So accordingly, if you want to reach this, it starts from this algorithm, start from root S, A, C, D. Again, this is the limit set in limit 2. So level 2. So here we could not find the goal node. So it move on to another path, that is B, from B to I, then to J. So finally it reached the goal node, that is J in this example. So this is the definition of depth limited search. Now let us consider the factors. One is completeness. So if we say this algorithm is completed or completeness, if the solution is above the depth limit, means it is possible to find the goal or to reach the goal within the limit, then it is complete. Next, time complexity is nothing but it is the order of BL. L is the limit, and it is space complexity is nothing but it is order of B into L. And with respect to optimality, it is not optimal. Why it is not optimal? Because if the goal is beyond the limit, or if the goal is not able to reach within the limit set in the algorithm, then it is incomplete, so it is not optimal. So suppose if it is able to find the goal within the set limit, then it is optimal. So these are the properties of depth limited search algorithm. In the next slide, we will see what are the advantages of depth limited search, and here it is memory efficient, and drawbacks are incompleteness, as we have discussed in the previous slide, and may not be optimal. These are the advantages and disadvantages of depth limited search algorithm. In the next slide, let us see the applications of depth limited search algorithm. One is path finding in robotics, and network routing algorithm, and puzzle solving in AI system, and game with AI, or game playing with AI technology. These are all the different applications of depth limited search algorithm. Students, so far in this session, we have discussed about 3 types of search algorithm. Let us continue our discussion in my next class. Thank you so much.